Hey guys, so today I'm going to be talking about this new field of physics that is attosecond physics, which is to me very interesting, and then it's also contributing to actually a lot of usefulness in our society in multiple fields, which we're going to see. But first of all, let's talk about the 2023 Nobel Prize, which really is, well, in physics, but really it's focused on the development in attophysics, which is based around these three very important persons. Pierre Agostini, Felix Kreutz, and Anne Louis. I might have butchered their names, but you get the gist. So these three people have basically developed a new method to sort of photograph um, things that are very small and moving in very, very fast time intervals, known as attosecond. And we're going to dive into that in just a second here. So first of all, let's take a look at the scale of our universe, of how things are around us, and take a look at the trend, right? So typically, the more mass an object has, the harder it is to accelerate it. I mean, it's not, well, that's true for all objects, right? Because of momentum. The more mass it has, the harder it is to accelerate it. But it's also going to be kept at speed easier. Anyhow, let's take a look at the Earth and the solar system and all these planetary systems. So every 230 million years, the solar system completes one orbit around the Milky Way. That is one orbit, and that is 230 million years, right? I mean, humans haven't existed for that long, so that's a very, very large time frame. Now let's look at Earth, right? We all know that every 1 year the Earth completes one revolution around the sun, and also every 27 days, which is, well, close to a month, the moon completes an orbit around the Earth. Right? Now let's zoom in a little bit. Let's take a look at, our brains, right? Every 5.5 hours, our brains, well, the signals in our brains travel the equivalence of one lunar orbit, right? So only 5.5 hours. You can see it's much faster than these more massive objects. If we're talking in terms of just, these neuron signals, right? And if we look at individual electrons, now they move in a very, very small time scale that is known as attoseconds. So attoseconds is 10 to the negative 18th of a second. That is very, very small. In fact, if you look at the universe in a scientific way, there are allegedly more seconds um, well, there are more attoseconds in 1 second than there are seconds in the entire existence of the universe, if you're saying that, it started with the Big Bang. Anyhow, so where does this come from? So typically, well, just for you to know the scale, light travels 3 angstroms, which is a typical size of an atom, in 1 attosecond. So light, well, that's the speed limit of the universe, the fastest thing that everything can travel at. It can travel around an atom or through an atom at about 1 attosecond. So yeah, that's about where the scale comes in. So just so you know that attosecond is indeed the scale of these minute particles, such as uh, atoms, such as electrons, and light. Okay, so before the works of these Nobel Prize laureates, um, we really understood the atoms only in terms of femtoseconds, which is essentially 1,000 times longer than an attosecond. So with these new discoveries, these new tools we have, we're able to really stretch that time frame and dive deeper into the details of the electron, atoms, and all of these particles. So why is it hard, first of all, to observe atoms and electrons, right? Because um, can we just zoom in, right? That would be the intuitive thought. However, first of all, to make an observation, we need for something to bounce off of the object of interest. We can't just, typically we need a medium that interacts with the object, right? So these, well, in terms of vision, right, we use photons, which bounces off of, say I'm looking at this camera right now, and I see photons that are bouncing off. I'm not really just directly looking at the atoms that makes up the camera. I'm looking at photons that, get absorbed and bounce off of the camera, right? And so is the camera observing me. That's how it observed me. It takes in these photons that's, you know, emitted by this lamp here and bounces me. It bounces off of me, and then it gets absorbed through the lens and transmitted into a digital format, right? And also, there's sound waves, right? You can this is more, I'm trying to say that it's not necessarily particles, but you can also be waves, right? Because I mean, if you think about it, photons are waves as well, right? But if we're just looking at waves, right? If you're hearing something, right? This microphone is now hearing my talks, and it's detecting my wave, which is oscillating with something in the microphone that gets transmitted into a digital format. So it's taking that thing that's bouncing off of my throat to observe my voice. So just the idea that you can't directly see anything, because that's not the definition of observation. We can't just look at the atoms directly, because there's no way we can do that. We need to have a medium to interact with it. So with that in mind, an observation also require two things. First of all, it's quick exposures. So we can think about this in terms of a camera, right? If we take a photo that's having a very long exposure, meaning it takes a very long time for the picture to be taken, right? So say like from the moment you press a button till the moment it actually completes taking a photo, it's, I don't know, like 1 second, right? What if you're taking something that's moving, right? And that thing is going to change how it moves within that second. So you're actually receiving different kinds of photons reflected by that object. So that's going to make the basically a longer exposure time is going to make the image or observation much blurrier, if you get my idea here. Yeah, so basically that, and also to make an observation, you need faster pulses. If a butterfly is flapping its wings, or a bird is flapping its wings, if you take a photo at the exact same time the wings are up or extended, you're not going to make much of an observation, because every photo you take is the same. There's not much difference. You can't see the other stages of the movement, and the only thing you can see is the single stage of that movement, and you can't really tell much by just that bird being in that one position. Maybe you can deduct by logic, but what if you don't know what a bird is, right? So quick exposures basically ensures that you don't have a blurry image, and fast pulses can basically guarantee you a clearer video. So, well, yeah, I guess that's a better way to say it, is that if you take faster pulses, it's more like a video. But if you're taking very slow pulses, it's more like you taking a picture every second or so. So obviously you can see that difference there. Anyhow, yes, so basically what I said there. Now, what about measuring things with light? And typically we use an X-ray to measure things, and that sort of worked out for us before, right? Well, not really, because let's take a look at a typical 5 megawatt, a typical 5 megawatt helium neon laser, which has a wavelength of about 632.8 nanometers, and it sends basically not one photon every few femtometers, which is, as we said, 1,000 attoseconds, about that, right? And you can see my calculations here going from energy to the numbers of protons per second. So yeah, these are not fast enough, basically, is what this is trying to say. So we need a better method. So first, let's take a look at the first laureate, that is Anne Lhuillier. And she basically discovered this thing called high harmonic generation back in the 90s, which is, it can be a long time ago, but it did take a while for all these things to kind of wrap up and get developed into an actual usable thing. So basically, what high harmonic generation is that when an atom is targeted by this intense laser pulse, such as an X-ray, it will actually emit the higher harmonics of the original beam. Right. So, so as we know, light waves are waves. They can be waves and particle. But if we're looking at them as a wave, they will have harmonics, which I'm going to dive into later. But the reason that that happens, so harmonics are basically the wave, but with a different wavelength. That is a fraction of the original wave. Anyhow, the reason that that happens is that when the laser hits the atom, some of the electrons from the atom will actually escape momentarily and then return or snap back into their original orbit. And when they snap back, their potential energy is decreased, and they're going to release energy in the form of a photon. And that photon released is actually going to be that harmonic laser pulse that gets detected. So this is what I'm talking about as with harmonics. And they're very similar to actually how an instrument works with overtones. So as you can see, we have the original wave on top there, and we have all these fractions of wavelengths, and they form these harmonics. So I just thought it's very interesting how all these waves actually relate to each other. We can actually think about these light waves in terms of sound waves. Okay, so how does this apply to attophysics, right? So she also found out that when you stack a number of these waves together, obviously they will have this constructive and destructive areas, right? So for example, that's how noise canceling headphones work, right? They play a wave that is deconstructive to all of the noises in the area surrounding you, so that they cancel out, so you don't hear those noises. That's the same thing happening here, right? So some of these areas get canceled out, and some of these areas stack up together to form a stronger wave, and that pulse is going to be much stronger, right? And it's going to be still having the speed of the wavelength. So now you're essentially having these pulses that are both fast and strong. Okay, so now we have some of the ideas, right? Some of the tools to potentially measure on this attosecond scale, right? As we said, we have this fast and strong laser beam that could actually go to that time frame and do some work there. But how can we ever calibrate it if itself is also in the scale, right? And that's where it comes to the second person, Piero Agostini. He basically developed a method to sort of calibrate this thing, right? So he deflected a part of the original laser wave, and by then he deflected like about half of the laser wave, and half of the laser waves go through the treatment, where they actually form the harmonics, and the other just bounces off, from mirrors, and then in the end basically measures the differences between the two laser beams times, and then with that he can calculate the pulse and width. There's a very complicated process which he goes into in this lecture of his, which I said in Source D, that he's given in Ohio State University, which is pretty interesting, but it's a bit too long and complicated, so I'm not going to talk about that here. But anyhow, also he discovered that the pulses are pretty much consistent, right? So the interval of these pulses and how strong they are pretty consistent in a wave and to a particular particle. And that is also good news, right? Because that means that it's pretty accurate. to be used as measurements. Okay, so what about some applications where actually it's better to use just a single attosecond pulse? And that's where the third guy comes in. I'm hoping I'm not pronouncing this too badly. Ferenc Krauss. Anyhow, he was able to actually isolate pulses of 650 attoseconds with a width known to 150 attoseconds precision by manipulating amplitude and phase. Again, it's a very complicated process, but basically we can see that we can just actually create a single pulse of things. So if you want to hit something, right, um, you can actually do that with a pretty good precision. Um, yeah, so that's his contribution. Okay, so now we have all these things. What have we just done? It's almost like we opened this door to a whole new world that is attophysics, right? So now we can, first of all, examine these electron clouds that has been bugging us for decades. Well, actually, it still will, unfortunately, because Heisenberg said the uncertainty principle. When you measure something by hitting, a light beam at it, it's going to hit that electron. So we can't really accurately measure it, but we can measure it at a much more precise time scale. So imagine if we're looking at a slow-mo video, if you're shooting it at 60 FPS, now we're shooting it at 1,000 times more than that. So what, 60,000 FPS, right? So that is a lot more accurate than before, which is really good because we can now take a look at how those electrons actually interact with each other and how they are situated in those electron clouds. And also, we can now actually manipulate electrons on a tiny time scale, right? And that really helps us with spectroscopy, which is fingerprinting the specific molecules, right? When you shine light through a molecule, it's going to emit different wavelengths, and different lights, and that is going to tell us, what type of molecule it is and what type of molecules there are in a mixture of something, right? And that is super useful, especially in medicine, in applied chemistry, and all that stuff, to actually know exactly what is in that mixture. Because, well, for a very long time, chemists have just been guessing, the exact percentage. You can't really know the exact makeup, right? You might know there's some, trash in your mixture, but you don't know exactly what they might be without doing a huge list of tests. But right now, with attophysics, we can more accurately determine what they are, with the said spectroscopy, right, scanning light through them. And also, more interestingly, this can be applied to ultra-fast electronics, which is where that single pulse comes in, right? So the photoelectric effect, which is basically the emission of a electron from a plate to another, when a beam of light hits one plate, right? Because there's more energy in that plate now. So now one electron gets emitted and it transferred to the other plate. So with these attoseconds pulses, we can make the photoelectric effect faster and more accurate, right? And that can be used to make ultra-fast transistors that can be used in computers, all these calculators, all these tech that can, really bump up that calculating power, and really helps a lot in, these new technologies, which is really useful. Yeah. And here are my works cited, and I hope you enjoyed my quick and short and not so detailed explanation, but hopefully interesting explanation of attoseconds, and how this new field of physics is pretty interesting, and how it can apply to our actually day-to-day lives. So yeah, thank you.